All right, so today we're taking a look at calculating the energy needed to change the temperature of a substance. Monday, we took a look at the energy when you're changing phase. So the phase of solid to the liquid phase. What's the energy to get from solid to liquid, to melt? Well, today we're going to change the temperature. So again, kind of a quick review. So quick review here. What we talked about on Monday is that your temperature doesn't change when you're going through a phase change. If you have ice at 0 degrees and you melt it to water, you'll end up with water at 0 degrees. And before your temperature starts to rise, all your ice should melt. So whenever you're changing phase, there is no temperature change. But here's the kicker. So here's kind of the kicker. Here's the take-home message for today. The temperature doesn't change when it freezes or melts, but you have to be at the right temperature for something to freeze or melt. If you have water at 20 degrees Celsius, it isn't going to freeze. Water doesn't freeze until you get it down to 0 degrees Celsius. Same thing with boiling it. You can't boil water if it's only at 20 degrees Celsius. It just won't boil. It won't turn into a gas. It won't go through that phase change. You have to increase the temperature. And again, that's kind of the point of what we're doing today, is looking at how much energy to increase the temperature, to bring that temperature up. So for water, and this is specific to water, other substances freeze and boil at different temperatures. But for water, pretty good to know this. The freezing melting point is 0 degrees Celsius. That's where water freezes or melts. Again, these are the same processes. Freezing and melting are the same thing, just one's going in one direction, solid to liquid, one's going in the other direction, liquid to solid. That's really the only difference, but otherwise they're the same process, require the same amount of energy, and they have to happen at 0 degrees. It won't happen at negative 10 degrees Celsius. You'll have solid water at negative 10, and it will not melt unless you get that temperature up to 0. Boiling condensing point, 100 degrees Celsius. So water boils at 100 degrees Celsius. Or if you have steam, it'll condense back to water at 100 degrees Celsius. Celsius is a much better scale than Fahrenheit. We don't have random intervals of numbers. actually the whole Celsius scale is based on water. They said, hey, it freezes at 0 degrees, it boils at 100. Every 1 degree in between is going to be 1/100th of the amount of energy it takes to boil water. It's a much better scale than the one we use, in my opinion. All right, so again, take-home message here. What we're working with today. If you have water and it's not at the boiling point, 100 degrees Celsius, doesn't matter where it is. And my example, I'm saying it's at 0 degrees Celsius. It's never going to boil. It doesn't matter how much energy you add. You have to get the temperature of the water up first. Ah. Again, we worked on Monday with how much energy to boil that water, or in other words, how much energy to melt the water, whatever phase change you're going through. But before you can do either of those, you have to get that temperature up or down to its freezing melting point or boiling condensing point. If you're not at the right temperature, it's not going to boil. Graph kind of showing you what we're working with today. So the graph we looked at on Monday was flat. As you added more energy, as you increased the energy, the temperature did nothing. It just stayed flat. We were changing phase. We were starting with solid, ending with a liquid. We're starting with a liquid, ending with a gas. We were changing phase, and as long as you're changing phase, all the energy you're putting in does not change temperature. You can add. It stayed flat. The temperature did not change. But today, when we add energy, our temperature is also going to go up. So as we go this way, we also go that way. Just like we worked with a couple of different variables on Monday to figure out how much energy would be needed to melt something or freeze something or boil something to change the phase. Same thing, same idea. There's a couple of different variables that influence how much energy we need to add to change the temperature of a substance. First thing, mass. How much of your substance do you have? Makes pretty good sense, right? Like, it's not going to take very much energy to heat up a little tiny droplet of water versus like an entire bathtub full of water. It's going to take a lot more energy to warm up that bathtub than it would just a little tiny droplet of glass. It's a much smaller amount of water. It's going to heat up a lot quicker. So the mass is important. The next thing that's important is the temperature change. That's a triangle. It's a Greek letter D or delta. In math and science class, we use delta, which again is just a triangle. We use that to represent change. So the change in the temperature, and again, that one makes pretty good sense, right? Are you trying to bring up the temperature of your water by 10 degrees Celsius or by 100 degrees Celsius? Which one? It's going to take a lot more energy to raise the temperature 100 degrees Celsius than just, a little old 10. So how much are you trying to figure out the temperature change? Oh, by the way, it is important how you calculate that. It should always be your final temperature minus your initial temperature. That should be your change. Why is that important? Well, because you can also go down in temperature. You can start at 100 and end at 0. That'd be a decrease in temperature. You'd have a negative temperature value, and you'd end up with a negative energy. And that's okay. You're allowed to have negative energies. Just means that energy is lost from the system. As water cools, it's losing energy, and we should report it as such by reporting it negative. So always subtract your final temperature, wherever you end, from your initial temperature, the temperature you started with. Watch your signs on that. And then finally, new variable here called specific heat, which we symbolize with a C. And specific heat is a constant, much like the enthalpies from Monday. Is a constant. It's unique to each substance. Each substance has its own specific heat. Not only that, not only does each substance have its own specific heat, but each phase of each subject has its own specific heat. It's like liquid water has a different specific heat than solid water, ice. Different specific heats. All right, so the formula we're going to work with in this chapter, this section, Q, there's our energy again. Amount of energy is equal to your mass times your specific heat times your change in temperature. So there's our formula. Questions? I'm going to turn the page here in a second. Good chance to pause. Make sure you guys got it all. Ask questions if you have them. People online? Okay. All right, so again, specific heats. They're specific to each substance you're working with. So like your homework tonight, I think one of your questions asks about a block of wood. Another question asks about a granite countertop. So those are different substances. When you have a different substance, I give you a different specific heat. I think one time even you're solving for the specific heat of aluminum or something along those lines. So if it's something other than water, I think I usually give you the specific heat. But water is such a common substance. We use it a lot for this material. Water is good to observe at attainable temperatures. We can freeze it and we can boil it. Most things we can't do that. But water is really good to work with. We can freeze it, we can boil it, we can see everything in between. So we love working with water. So for water, we'll take a look at that. The specific heat of ice, that says C of ice, specific heat of ice is 2.1 joules per gram degree Celsius. So what that unit is saying, yeah, there's quite a bit there, but yeah, you got to write it. Units are important. What that's saying is that it's going to take 2.1 joules of energy to raise 1 gram of ice by 1 degree Celsius. That's what that unit states. Liquid water, a little bit different specific heat. It's 4.18 joules per gram degree Celsius. It's almost twice as much energy to raise 1 gram of liquid water by 1 degree Celsius as it is to raise 1 gram of ice by 1 degree Celsius. And then finally, water vapor we also call steam. So the specific heat of steam, 1.9 joules per gram degree Celsius. So there are the 3 specific heats for the 3 different phases of water. Okay, as you can see, it's actually easiest to raise the temperature of steam as compared to the other 2. So steam is the easiest to change its temperature. Hardest to acquire energy-wise, but easiest to change temperature once you have it. Questions so far? Doesn't look so bad, does it? Pretty doable? I bet you guys get the picture pretty quick. I'm going to do a couple examples with you and then set you loose. So first question, how much heat is required to bring the temperature of 25 grams of water from 0 degrees Celsius up to 25 degrees Celsius? Heat, just another word for temperature. Excuse me. Heat, just another word for energy, not necessarily temperature. Sorry about that. Heat, just another word for energy, excuse me. So how much energy? So we're looking for our Q. Q question mark. We're going to need a mass, we're going to need to change temperature, and we're going to need a specific heat. So our mass, we have 25 grams of water. Our specific heat, sometimes you got to think this through. This one's pretty straightforward, but sometimes you got to think it through. We're at 0 degrees, we're going up to 25. What state of matter is water in from 0 to 25 degrees Celsius? We just talked about it in the last page. Ice melts at 0 degrees. So that means if it's melting, then you're now in liquid, and it doesn't boil to 100. So from 0 up to 25, you're going to be in the liquid form of water. So there's the one we want. And then our temperature change, our delta T, always do final temperature minus initial temperature. So our final temperature, we're going up to 25 degrees Celsius. We start at 0 degrees Celsius. I don't know if there's a typo. I don't know if we forgot to add the 0.0. We'll work with it though. Not being that it's not 0.0 means there's only one sig fig and it's in the ones column. So we're actually going to lose a significant digit there. The ones in the tens column. We'll see if that affects our overall answer or not. But just 25 degrees Celsius is our change in temperature. We actually lost that 0.0. All right, let's set this bad boy up and let's solve for it. Our formula is Q is equal to mass times specific heat times delta T. We have a mass, we have a specific heat, we have a delta T. We're looking for Q, that's perfect. Our formula is set up already. We have the variable we're trying to solve on the side by itself. We're good. So let's plug in our variables in, 25 grams, 4.18 joules per gram degree Celsius, and 25 degrees Celsius. Okay, there we go. Grams will cancel out because on the bottom, it's on the top, so that cancels out. Degrees Celsius cancels out. It's on top, it's on the bottom. The only thing we're left with is joules. That's good. Q is measured in joules. Q is heat. Q is energy. So let's plug this in then. Pretty straightforward. 25.0 times 4.18 times 25. 26125. 3 significant digits. 3 significant digits. Just 2 significant digits. Man, so that subtraction step did play a role there. Just 2 significant digits. So I just want the 2 and the 6. The number after the 6 is not enough to round up. So I'm just going to call it 2600. And I can't just round that 1, 2 off and say it's 26. That'd be different. But 2600 joules is my answer. There we go. 2600 joules of energy. Not really that much. Might sound like a lot, but a joule is a really small amount. It's not that much energy, which makes pretty good sense too, because 25 grams of water is not that much water. You have like a water bottle of water, like Dasani or something. Those are like 350 grams of water. So 25, not that much water. Not that much energy. Questions? All right, one more example for you then. A little different problem here. How much steam in grams, so we're looking for a mass, will release 805 kilojoules of energy when it drops from 150 degrees Celsius to 100 degrees Celsius. All right, well, this time they gave us Q, 805 kilojoules, 2 things. One, if that energy is being released, what should my sign be? Yep. If you give something away, if you release something, you lose it. Losing, negative. So yes, there's a negative sign there. Should be a negative sign. Good. Second thing is that's in kilojoules. All of my specific heats are in joules. So I am guessing I want to get rid of that kilojoules. We can do that pretty easily. You know how to work with the K. 1 kJ, 1000 J. There's negative 805,000 joules of energy. It sounds like a lot. That's a decent amount. It's a decent amount. It's not a huge amount. Again, a joule is a very small unit, but negative 805,000 joules. Okay. How about a mass? Well, we don't know that. That's what they're asking for us to find. So if we don't know a mass, specific heat, well, it's telling us we're working with steam, but also we can think through it. We're going from 150 down to 100. Anything above 100 has to be steam. Liquid water doesn't exist above 100. Or we would have stopped and phase changed it. So yeah, we're definitely working with steam. That specific heat is 1.9 joule per gram degree Celsius. And then finally, our change in temperature. We're going from 150 down to 100. Remember, final minus initial. Our final temperature is 100 degrees Celsius. We started at 150 degrees Celsius. That means our temperature change is negative. And that's okay. It's supposed to be. We've got a negative energy and a negative temperature. Those two should cancel out to give us a positive mass. All right, so we got our variables. Let's set up our equation and solve it. So we'll find our energy by multiplying our mass, how much water we have, by the specific heat of steam, because the water is in the form of steam, times how much temperature we want to change it by. Well, we're looking for mass, so we got to get that on a side by itself. The way that we do that is the opposite operation of what's going on. So if I'm multiplying it by the C and delta T, I'm going to divide both sides by C and delta T. That gets my mass on the side by itself. Now I'm ready to solve for it. Again, my negative 805,000 joules. My 1.9 joules per gram degree Celsius. And my negative 50 degrees Celsius. And those will give me my mass. So joules cancels out. It's on the top, it's on the bottom. Degrees Celsius cancels out. It's on the bottom of the bottom, which basically means it's on the top, you know, it's a double negative. So it's on the bottom of the bottom, it's on the top and on the bottom. The bottom top cancels out. And then we're left with grams on the bottom, which basically means on top, which is good. That's what we want. We want grams since we're looking for a mass. Cool. Hey, big thing, guys. I've said this many times. Most of you guys are doing an excellent job listening to me. I appreciate it. Good work. Keep it up. But some of you still aren't. You just aren't hearing what I'm saying, not understanding what I'm doing. I'm not sure, but you aren't doing it correctly. Negative 805,000 divided by 1.9 divided by negative 50. A lot of you are still hitting times right there. Don't. I know, I get it. It says times, but guys, that negative 50 is on the bottom. Do not multiply it. You will get a very wrong answer. And again, a lot of you are, not a lot, but a number of you still are doing that. And it's just, destroying your answers. If you insist on hitting that times, like I see at times you have to enter it, well, okay, put that number into parentheses in your calculator. Because otherwise your calculator is going to follow order of operations and it's not going to divide. So watch that. It's still a very common mistake, and it's not a mistake you guys should be making. So watch that, be aware of it, careful. There's our value. 3 significant digits, just 2 significant digits, and 3 significant digits. I'm going to be limited to 2 because of that 1.9. So the 8 and the 4, that's it. The number after the 4 is a 7. That's enough to round it up. So we'll call this 8,500, nope, not joules, grams of water. It's a decent amount. 8,500 grams. A little over 20 pounds of water. So almost 3 gallons of water is what that would be. So good amount of water. Questions? Comments, concerns,